we're going to have the full characterization of dc of Tn. And I mean, once we have the full characterization of dc of Tn, then we can also, we can also see that, and I'll start giving you definitions. So once we are done with the proof, I'll give you also some discussion on extensions of these results to bigger sort of like bigger setting or more generalized setting, whatever that means. And we're gonna give the definition of C, so-called C0 and also H bar, whatever that means. I mean, we're gonna go through that in a timely manner today. And as always, again, I mean, stop me, discuss with me, or fill me in with anything that you feel like it's not clear. All right. So I quickly recall the sort of the setting we did last time here. Again, I mean, the set of assumptions in this section is always the same. L and H are smooth enough, superlinear, and locally uniformly convex. And the result we proved last time was that if U is in DC of Tn, then we have proved that U is Lipschitz, so it's differentiable almost everywhere. And at points of differentiability, we have shown that h of x du is less than or equal to c. Okay, so that's we proved. It's clearly an important characterization of DC, right? So maybe let me just write out a quick summary here. So we have proved that if U is in DC of Tn, then we implies that U is Lipschitz and h of x du x is less than or equal to c almost everywhere in Tn. Okay, so those are two results. I mean, two parts of the result, Lipschitz and less than or equal to c almost everywhere. So I mean, for today, we're gonna obtain the converse claim. That is, I mean, we're gonna also show that if U is Lipschitz and it satisfies the property that h of x du x is less than or equal to c almost everywhere, then you can conclude that U is in DC of Tn. And this is, again, I mean, in many applications in various different areas, this seemingly beautiful and simple result is kind of a big thing. Why is it a big thing? Because the second claim is about a PD claim, right? The first claim is about like a claim in the Lagrangian framework. So it's rather striking. And now you see that every building block is pretty natural and simple, but I mean, once you put everything together, you have quite a beautiful set of tools. Okay, so that's what I recall. So I mean, this is exactly what I wanted to prove today, and then we discussed certain new definitions and certain generalizations and stuff like that. So that's the red box I put on the left panel. So we're gonna show that if U is Lipschitz and I have this inequality almost everywhere, then we have to show that U is in DC of Tn. Okay. And I think that we actually have discussed this idea of roughly a while ago. I mean, I did throw in kind of a quick proof to you, but I want to recall it because this is one of the simple but central idea, that occurs in lots of places. So the key point here, or the key difficulty, is that U is only Lipschitz, right? Of the lemma in the red box, I'm summarizing of what is the key difficulty. So only Lipschitz and clearly not smooth enough, right? And in particular, du might have jumps. So that means that we need to be careful. And I mean, in terms of jumps, last time we already gave such an example, right? You take u to be, just like this, for example. Then you see that du in this case is just u prime, right? So you see that u prime jumps between -1 and 1, right? And then vice versa. So there's a gradient jump. So, du doesn't change in a expected way, in a continuous way. So we got to be careful when we are dealing with the analysis. So a natural way then the typical way, a typical way for dealing with this in terms of analysis is that we need to smooth you up. Okay. And in general, this is not easy at all. Okay. So in our setting, what helps us is that we exploit the convexity of h in P crucially. Okay, so I want to emphasize this because after proving the result, I will discuss with you certain generalizations, and then when we cannot do that, so we really need to exploit very crucially the convexity of H and P here, and as an analysis tool, I mean the tool that we are using is just a one of the simplest tool in doing things, is just to smooth things up, right? So we are gonna smooth things up by using convolution idea. Okay. So basically, I mean, of course, I mean, it's sort of clear when we write out the analysis, but convolutions here means what? I mean, roughly speaking, you take for example, if you have, I mean, it's a good thing that I drew the earlier picture here. So for example, if you have this function, this is u, that is not smooth enough. So what we do is that we take a kernel, right? I mean, I'll explain eta epsilon or something like that. What we do is that we take a kernel eta epsilon of these types, okay? And we sort of like shift it around, right? For example, if I'm centered around the point x here, then if I take the integral of eta of this kernel with respect to u, then I have the approximated value. So u epsilon of x is essentially eta epsilon convolute with u at x. But I mean, the geometric meaning is important. It's very simple. Of course, if you have seen that, I'm just explaining very quickly. So what you are doing is that you are taking this sort of kernel, you're shifting it around at a given point. You're trying to take the average, right? I mean, this is the weighted average. I mean, the integral here is just the weighted average. This is integral in Rn at the epsilon x minus y uy dy. So you're taking essentially the average. So for example, at the point x, I'm taking the integral here is just 0, right? Because everywhere is 0. So I'm shifting it around, shifting it to the next point. So around here, if this is the next point, x bar, then I see that if I'm having a linear speed, I'm taking the weighted average. If the kernel is sort of symmetric, then the values there is still having slope 1, right? And you keep shifting it around, everything is fine, if you are shifting it around like that. Um, but let's say at this tip, in which you have the jump in the gradient, right? So you're putting a convolution kernel here. What you're doing is that because you are taking the weighted average, you're sort of like, instead of having the kink, you're smoothing it up, right? So eventually, I mean, after this process, you have the function u epsilon, which gonna look like, you know, roughly speaking, this is 0, this is 1. It's gonna look like this. So you're smoothing it up here, going up. So, and then you're gonna smooth up at the kink and then go down like that. So this is u epsilon. So you're smoothing it up at 0, 1, and 1/2. Okay, and you see that the at this corner, instead of having the gradient jump from -1 to 1 directly, then by smoothing it up, you have the gradient here change in a smooth way from 1 to -1. Okay, so that's a very simple idea. Of course, you have seen that in analysis, but I just want to convey the message here that I mean, if you see that geometrically, then it's rather natural. Okay, so let's focus on the proof, and then we discuss crucial things in the proof and generalizations. So I'm just gonna smooth it up by using modification with the standard modifier. So I'm highlighting things on the left panel here. So you take a normal convolution kernel, so just eta compactly supported in just a ball of radius 1/3 or 1/10, whatever. Its integral is 1. Sometimes, if needed, you can require it to be radially symmetric or not, depending on your purposes. And then you are scaling it, right? So once you scale it, you take eta epsilon is 1 over epsilon to the power n, eta x over epsilon. So you scale it, you have it sort of going steep up and down. It's essentially like a bell curve. Not really, because it has compact support, but so the key thing now is that once you scaled it, the support of eta epsilon is going to be in a ball of radius 1 epsilon over 3, right? So that's rather small. The integral is still 1 because you are divided it by 1 over epsilon to the power n. And then this was the definition I wrote down earlier. You take this convolution. And I mean, clearly that u epsilon is smooth. U epsilon converges to u uniformly on the torus. Everything is still periodic, no problem. So this is the new idea in our course. And again, I mean, as I recall, we have discussed this quickly in a lecture a while ago. But I mean, what we do is that we recall that. So you recall that you have h of y dy, duy is less than or equal to c almost everywhere in the torus. So I mean, because this happens almost everywhere, you can do integrations, right? You recall that you know integral in Rn of eta epsilon of x minus y dy is just 1, right? So you are just integrating this one with something less than c. So the whole integral is less than or equal to c, right? All right. So now I'm gonna use crucially, so use the fact that P maps to H of X. P is convex, and I'm using the Jensen's inequality. Okay. Because convexity helps me to use the Jensen inequality. Surely I'll recall that with you in a sort of elementary and deep way. I'll explain why, but let's do the proof first. So, I mean, one of the key things there that you see on the left panel, I'm trying to squeeze, let me try to highlight it. I'm trying to squeeze this integral to the thing inside this du y here. So that's what I'm trying to do, because I'm trying to do Jensen inequality. What is not so convenient for me is the fact that I have the y here is running with respect to dy. So when it's running, then I can't just use the Jensen inequality, so I would have to fix it. And the idea is they want to fix y to be x. So x is not running in the integral, right? So that's the idea. So now I recall now that because support of eta epsilon of x minus y is just about the ball of center x, radius epsilon over 3. So I'm rewriting the integral to be like that, natural. And then, I'm changing, as I promised, I'm changing the slot y here to be the slot x, right? So I'm switching y to x, and then I know that my Hamiltonian is Lipschitz in the x variable. So, I'm just using the inequality that h of y duy is greater than equals to h of x duy minus c times x minus y. And this is good because, y is not so far from x, right? Y and x are of order epsilon. So I can estimate that c of x minus y is less than equal to c times epsilon. And that's why, when we do convolution, we use the fact that it has compact support because of that. So that's good. I have been able to change my integral to the one that I'm highlighting here. This one is good because of the fact that, x is fixed. The only y that are changing in this slot and in this slot, right? Right. X is a fixed thing, and then surely I have to pay a price of c epsilon, which is okay. It doesn't matter. Okay. Now I'm gonna use the Jensen inequality. Okay, maybe let me record here. So so a simplest form and then generalized form. So simplest form of Jensen's inequality, right? The simplest form is because of convexity, right? So I can write like h of x p plus 1/2 of h of x plus p plus h of x q is greater than equals to h of x p plus q over 2, right? That's the simplest form that you have seen. And actually, this form is equivalent to all the other forms. It's just a definition of convexity, right? And a bit more general form is that if you take like any convex combinations, it's going to be greater than h of that convex combination, right? So if you take the indices alpha 1, alpha 2 up to alpha k and non-negative, and then its summations is 1, and then you would have that summation of I from 1 to k, alpha I h of x pi is going to be greater than equals to h of x summation I from 1 to k alpha I pi, right? So that's the next form. So let me highlight them. The first form was this sort of like just convexity form. The second form is this one that I'm highlighting here, that is a little bit more general, right? It involves that if you take a convex combination of the Hamiltonian, it's going to be greater than the Hamiltonian of that convex combination, right? And indeed, if you recall that integrals are nothing but sort of like summations, right? Because I mean, you can approximate integrals by finite summation and pass to the limit. And clearly that, the crucial fact here that you're using is the fact that the summations of the alpha I equals 1, which means that, if you take, so a more general form, so this is let's say that a very useful form. I wouldn't say that it's the most general form because, a very useful form is that if you take gamma to be functions gamma to be non-negative and smooth enough, and integral in Rn of gamma y dy is equals to 1, then you would have that You know, so you take integral in Rn of gamma y h of x uh, py dy. Okay, so you can, you know, again recall that this gamma y and py plays a role of alpha I pi above, right? Again, by approximations and things like that. So you have this is greater than equals to h of x integral in Rn gamma y py dy. Okay, so that's that. I mean, actually, I just gave you a proof because, you know, everything here we are dealing with just a normal Riemann or Lebesgue integrals, nothing more than that. Let's say Lebesgue integral. Okay, so it's a very detailed explanation. Do let me know if it's something is vague or unclear. So that allows me to squeeze in the integral inside the h, right? Because of Zen that I just explained here, this one. Okay, so, and this is good because once you can put the integral inside, then this is nothing but just du of epsilon, right? So you have been able to smooth u up by u epsilon, and you have been able to squeeze the integral inside to have that you can evaluate h of du epsilon of x. Okay, and you have to pay the price of c epsilon, but that's not a problem. Okay, so at the end of the day, after this approximation step, we got to the point that we have this box. That is to say that we have h of x du epsilon of x is less than or equal to c plus c epsilon. Okay, so this is not quite c, but I mean approximately c, right? And then u epsilon is now smooth, right? One is smooth, then you know you can do the normal computations, because earlier I'm afraid to use chain rule. Du can jump, so I'm not sure if what I'm doing is right, because you see that I have this term here I'm highlighting here, du epsilon gamma s dot with gamma dot of s. If du is only measurable, then I got to be very careful with with writing down what I have. Actually, I might not have chain rule, right? But u epsilon is smooth, so I can just use the normal chain rule. I'm writing it down like that. And again, I mean, you can take gamma to be piecewise C1, that's fine. And you see that by the sort of usual duality inequality, we can write to be like that. L of gamma dot is just the action functional. Okay. What is a little bit different is that I have h of gamma s du epsilon of gamma s. This is not less than or equal to c, but it's less than or equal to c plus c epsilon, right? So we have to pay a little bit of the price. This is not a problem. Anyhow, so we got that u epsilon of gamma b minus u epsilon of gamma a is less than or equals to integral from a to b l of gamma dot ds plus c b minus a. So this is the normal thing, right? And then we pay a bit of the price, so we have plus c epsilon b minus a. Okay, so that's what we got from here. Okay. Well, the key thing is that the key thing is that this part that I'm highlighting here is exactly what we want, right? Okay, we do pay a bit of the price, but because this is a normal step in analysis, right? You do approximation, you let epsilon goes to 0, then you can have that the error term goes away. So you end up with exactly the normalized action functional L plus C. Okay, so we are done, right? We have got that U is bounded by L plus C. Okay, so you see that the interpretation of U is bounded by L plus C is sort of a Lagrangian platform, right? Just saying that U is dominated by this action functional, but we have been able to show that this point, the point that I'm highlighting up here, is that this point is only about U is bounded by L plus C. So only about bounded by an action functional for any two given points. Um, but we have been able to characterize that that's equivalent to a sort of a PDE in the almost everywhere sense. And that's really remarkable. Okay. So that's the proof. So you have seen that actually without convexity, right, without Jensen inequality, then actually it's really hard. It's not, it's not something like doable, and actually it might go wrong, right? Um, so so let me make some remark. Maybe let me just write this one down. I'll ask you if you have questions. So the first remark is that convexity seems extremely crucial. Yeah. Okay. So do you guys have any questions or concerns for me up to this point before I moved on to discuss some related parts? Any questions or concerns or things you want to discuss?
Can I ask two quick questions?
Mm-hmm.
So the first one is, I think when U is Lipschitz, we have chain rule and like fundamental theorem of calculus for
Um,
everywhere points.
okay. So so remember that if U is Lipschitz, then it's not differentiable in a set of measures zero, right?
Mm-hmm.
So the part gamma can easily go on that whole set that U is not differentiable,
Okay.
right?
But still, it's like differentiable almost everywhere.
It is differentiable almost everywhere, sure. But okay, so let me give you this example. Um, so let's look at the graph of U in this V shapes, for example. So you have this graph. Okay, this is the graph of U in 2D. Okay. So U is differentiable everywhere except this piece that, I don't even know how to define the gradient of U, right? So it has a gradient jump. So what if your curve is going from gamma A to gamma B here? Exactly on the lines that U is not differentiable. Does that make sense?
Okay.
Yeah. So remember that we are doing when we are dealing with the action functional, we are dealing with curves, and curves, if they are nice, let's say, piecewise C1, and they only of Hausdorff dimension one, right? And when U
Mm-hmm.
is only differentiable almost everywhere, it might not be differentiable in a set of measures zero. That can be rather complicated, and your curves can easily just stay entirely on the places that U is not differentiable.
I see.
Yeah,
Okay.
but yeah, sure. That's a very important question. Uh, yeah.
I see. Another question is, I think in the whole proof, you didn't use U as Lipschitz. I think only U is continuous is enough.
Uh, okay, so so the key point here, the key points here is that in order to have that h of y duy defined almost everywhere, I'm using already the fact that duy is defined, right?
Okay, okay, I see.
So duy is already defined almost everywhere, and the
Mm-hmm.
fact that duy is bounded is just because of the assumption I put from the beginning that h is superlinear.
Mm-hmm.
So yeah, so if duy is not defined almost everywhere, then I cannot do this integral. I mean, I'm having trouble with interpreting what is h of y duy, right? Here I'm interpreting it as an L infinity function. Uh, so that's why I can do integrals.
Okay, I see. Thank you so much.
Okay. Yeah, good. So I mean, Very good. And keep asking question. You see that sometimes things are quite delicate and subtle here. It's sort of like, for example, if okay, we are only dealing with first order equations. If this one is moved to second order equation, actually it's very hard. It's only done a few years ago by my group. So it's not something that you can treat it without care. And you see that Fatih's book, it's was only finished around 2010. Up to this moment, I don't know if it's published or not. I mean, some points it was said that it's published in Cambridge University publisher, and some point it's not. So I don't know the status of it at this moment. Uh, anyway, um, so so um, so actually, I also want to discuss this thing that some of you actually have also asked me, like, to what point that you can relax the convexity assumption. So I want to say here is that this result still still holds when p maps to h of xp is a level set quasi convex. Okay. um so level set quasi-convex, I mean, we have not discussed about this at all. And I said from the beginning that I'm going to be a little bit, sketchy here. I didn't discuss much about quasi-convex function, but roughly speaking, quasi-convex functions are functions that, let me write out the definitions. So you would have that for h of the fixed x, uh, for h fixed x in the torus, we would have that p, so that h of xp is less than equals to s is convex for any s in R. So its sub-level set is always convex. And quasi-convexity, maybe not in physics, but it's I don't know. I mean, I shouldn't say that, but at least it's extremely important in PD and also in economics. Many functions in economics are quasi-convex, level set quasi-convex. So when you draw a quasi-convex function, it might not be convex. It can be like this. So this is a prototypical example of the function that is quasi-convex. What you do is that you cut off any s, any uh, height, then its sub-level set is convex, right? So its sub-level set is convex. Huh? So this result still holds true for quasi-convex functions, and not always that you have a result that holds for a uniform convex case, and it holds for level set quasi-convex case, because it's weaker than convexity. But in this particular instant, it holds. And let me tell you quickly why. This is rather interesting. I mean, I don't know. So why, right? Uh, why then? If you look back, and also, like, because of the question that you see asked, you can see that what we have done is that we have used the fact that it's defined almost everywhere. Then you can integrate that with the modifier, and I do need integration with the modifier to start with. So clearly, everything seems to hold except the fact that I have to have something to substitute for the Zensen inequality, right? Okay. So how do I do that? So clearly, the key point here that I would need to discuss is that what is a generalized or substitute version of the Zensen inequality? It turns out that there's still a version of that here, and again, it's quite important in economics. So a generalized version of the Jensen's inequality. Okay, so let's do it first for 2 points, right? So what would it be? So so the simplest case would be that if I take h of x, p plus q over 2, how do I compare that with h of p or h of q, right? I don't know, right? So let's see. If let's take this picture up here. So if I take this one to be p, this one to be q, this is maybe not a very good representative picture. Fine, whatever. Okay, so the key thing here is that because there's a sub-level set of H is always convex. So if I take P and Q in the sub-level set S, then surely P plus Q over 2 is also in the sub-level set S, right? So naturally, this suggests me that I have this substitute inequality. Instead of less than equals to the average of H of P and H of Q is less than max of H of P, H of Q. Okay, right? Because max of H of P and H of Q is the sublevel set S, and clearly if P and Q are in the sublevel set S, then so is P plus Q over 2 because the sublevel set has to be convex. So that's the substitute inequality for the level set quasi-convex case. And again, this inequality is used a lot by analysts, PDE people, and economists, and maybe some other fields that whatever. So then the some more general versions, so general versions of this inequalities is that if you take same as before, so let me see, what did I use here? Alpha. So if you take alpha 1, alpha k greater than equals to 0, summation of alpha I equals to 1, then you would have that h of x, summation I from 1 to k, alpha I pi is going to be less than equals to max of h of uh, pi for 1 less than equals to I less than equals to k. Okay. So just replace the average or the convex combinations by the max. And that's the first version. So the second version is that if you take gamma to be greater or equals to 0, integral in Rn of gamma y dy equals to 1, then you would have that h of x integral in Rn gamma y py dy. This is going to be less than equals supremum of y in Rn of h of x py. Okay, whatever that means. Again, it might be hold on, I gotta be careful here. Y in Rn intersect with the support of gamma. Okay, depending on the support of gamma. Okay, and I claim that with this we are done, because you can look back at the inequality we are using. Where was that? Okay, so what changes is only this part. Let me put a box here. What changes is only about this inequality, right? Where's the Jensen inequality? Okay, it's only here in the box that I'm putting on the left panel. Instead of having the h of the integral inside, you can just write to be supremum of h of x duy, right? And that one is essentially of the size of c plus c epsilon as well. So that's exactly what we would have, and we are done. Okay, so I still remember this because when a long time ago when I was giving a short course on this thing in at the University of Tokyo, maybe I don't remember, maybe 7 or 8 years ago. Then I was also talking about the quasi-convex case, and at that time there was some results being written down, but there was a student of Giga that was really interested in this, and he could characterize deeply about this quasi-convexity, and could use this sort of points in discussions to write a short paper on this. So it's quite interesting. What I meant is that some results were written about quasi-convexity only in 2014 or 15. So anyway, so that's that. Any further concerns or questions for me on this? Is it clear? Okay. Great. Again, do ask me and discuss with me if you have concerns. So this is, now we have a very clear characterization of DC of Tn that I'm highlighting it here. And maybe let me make a remark. Remark is that we just show that this also holds if H is only level set quasi convex in P. Okay. Again, not always that we can have an analog version in the quasi convex setting. Okay. So now we are ready to define a central notion in this course and also in various different fields. Some of you here have been working on homogenization, so you know what I meant. But if you haven't, no worry. We're gonna touch upon that later. So we have seen that with h of x du is going to be less than equal to the essential supremum of that, right? For any u, again, u is, I take it back, u is for any u Lipschitz, and it's defined almost everywhere with gradient bounded. I can define cu to be essential supremum of that. And clearly that I have h of x du is less than equal to cu almost everywhere, right? So for any Lipschitz functions, I know that u is bounded, dominated by L plus cu. And again, cu is this thing up here. So what we are doing is that for any Lipschitz function that we say that we can find such a cu that u is dominated by L plus cu, and then we're gonna define a constant named C of 0. So I'm following this notion. This is in Fatih's book. So, or in dynamical system, people sometimes call this one C of 0 or alpha function, whatever that means. And this is in the context of dynamical system, is written first by Manic, a top expert in Hamiltonian dynamics. So in dynamics, people say it Manic critical value. So what you define is that you know that for h of x du is going to be less than or equal to some c, right? C is like cu above, and you're trying to find the smallest possible constant. So you're taking infimum of all possible constant. Okay. And you know that by C of 0, and you say that in dynamics it's said to be Manic critical value. In the PD language, it was defined by Lyons, Papanikolaou, and Varadan. Lyons is Pierre-Louis Lyons. Uh, uh, Papanikolaou is Josh Papanikolaou at Stanford, and Varadan is Varadan at Courant. So they define that one to be the effective Hamiltonian, and also that in both of the languages there's another notion called ergodic constant, that whatever. It's defined to be just the ergodic constant. So I'm out of time now. I have few minutes, so I'm just gonna say this one quickly. C0 is finite. That is clear, right? Clearly that is bounded by a constant cu. You just take u to be a Lipschitz function. You can find cu here, cu up here. So it's clear. I'm writing on the left panel now that cu is finite, right? Why is it clear that it's finite? Because because du is bounded, right? U is Lipschitz, so you take h of x and some vector bounded, and you take the essential supremum, it has to be bounded. So Cu is finite, okay? And C0 here, you are taking the infimum, right? Of a bunch of things. So clearly it couldn't be infinity because it's already bounded by something, okay? But you gotta be careful that it's not minus infinity, right? Why is it not minus infinity? Well, remember that our Hamiltonian h of xp is superlinear, right? So we always have that h of xp is greater than or equals to some minus c for some big C for all xp. Therefore, we should imply right away that c of 0 is going to be greater than or equals to this minus c, right? Because you, when you take essential supremum here, it's got to be greater than or equals to minus c always, okay? So that's good. So we have C0 is finite. And now it comes to be a notion. This is the object called effective Hamiltonian. So I should have said that in dynamical system, in the whole Fatty's book and in with KM theory, typically people would consider only C0. So only the Manic critical value or the ergodic constant at 0. But in the PD language, it turns out to be useful that you vary the P. Um, and also actually in classical KM theory, I should be clear. So in PDE and classical KAM, so Kolmogorov Arnold Moser theory, it's important to define h of p, so h bar p at any fixed vector p, right? So you fix a vector p, and then you would consider it to be infimum of all c in R, so that there is a Lipschitz function w in Lipschitz of Tn, so that you have h of x p plus dwx is less than or equal to c almost everywhere in the Tn. So what we are doing here is that we are just squeezing the vector big P. So you just vary your Hamiltonian to that vector big P and you consider that. So in particular, here we have h bar of 0 equals to c of 0. Okay. Um, but this object h bar p turns out to be very important. You can for fun, you can verify quickly. I mean, we're gonna get back to this point much later. I don't think I have a lot of time for that, but you can verify quickly that h bar is convex. Okay? You just use this definition, verify very quickly because h is convex. So you just use convex combinations, verify quickly that h bar is convex. And I can tell you that that a major question, that is a major open problem, is to study the properties of h bar. That's a major open problem. There have been some preliminary results and some good enough results on studying h bar, but not so deep. I mean, you can see, I mean, most of the up-to-date results are in written down in my book already, and not many. I mean, it's still a really mysterious object. It got to be understood and studied much deeper. And for those of you who have known KM theory or are from, sort of celestial mechanics or something like that, let me tell you that h bar p is the key thing here, because eventually, or roughly speaking, what you're gonna have is that you're gonna have h of x p plus du of x and p, u depend on x and p, equals to h bar p. Okay. So roughly speaking, you're gonna have this kind of equations. We're gonna get back to this point much later in the class. So you have this one, So what we are doing here is that we start with the Hamiltonian h depending on x and p. So depending on two n variables, we don't know whether it's integrable or not. After doing this, we are switching from this one to this one, which is, so this one is integrable, right? The second one is integrable. So you're gonna have the Hamiltonian OD is integrable because it's only depending on the momentum, and this U here is nothing but is a canonical transformation. Okay, so this is coming from KM theory, classical KM. But okay, uh, again, this is not in the perturbative setting. This is in a general setting. So to understand this viewpoint, actually, is very hard. You have seen that to have canonical transformation and stuff like that, you has to be smooth. C2 or something. In this case, we're gonna see that U is only Lipschitz, so that's gonna be a big problem. But I mean, forget what I'm saying here. We're gonna talk much about this, but for now, I'm hopeful that today you see the new definition of C0. That's extremely important. You have seen the clear classifications or characterization of DCTN, not only for the convex setting, but also for the quasi-convex setting. And I think that they are remarkable. And still, I mean, there are lots of research going on. For example, what happens if H is not convex at all? Can you do something for that? That's widely open. Or can you characterize some properties of H bar P? That's also widely open. And we are quite up to date on those aspects. I mean, we're gonna need to go further on other things, but I think that's good for now. Any quick question for me? Okay. So if there's no questions, I mean, we got already quite great discussions earlier already. So thanks a lot for the questions and for the discussions. And I'm hopeful that we can always discuss like that. So if not, then I'll see you on Wednesday. Bye for now. Thank you.